Predators eat prey and prey try to run away from predators. There are models that describe how these populations impact one another, and an interesting pattern seen in these models is that the populations tend to oscillate. The y-axis on this graph indicates the population of a species, and the x-axis indicates time. So the graph shows how the population changes over time. In this case, predators are red and prey are blue. This oscillation happens because of a cycle. First, prey populations increase. This means more food for predators, which leads to more offspring and thus more predators. The growing population of predators eat more prey, thus the prey population decreases. A decreasing prey population means less food for predators, which decreases offspring and thus the predator population. Less predators mean less prey are being eaten, so the prey population increases, and the cycle continues on and on. So I tried to create a predator-prey model, but my first attempts looked nothing like this. To understand why, let me explain how my model works. On the left is a map of a circular environment. Predators and prey can exist on any of the squares within the map. Red indicates that there are predators on a square, blue indicates that there are prey, and purple indicates that there are both. The darker the color, the more individuals there are on the square. Each iteration, predators try to move towards areas with prey, and prey try to move towards areas without predators. If a predator ends up on a square with a prey, it will eat one of the prey and give birth to a new predator. Each iteration that a prey survives being eaten, it has a chance to give birth to a new prey. In the first simulation I made, the predators end up eating all the prey, then they move around pointlessly. It doesn't make sense for the individuals to live forever, so an easy improvement to make is to add an age limit on both predators and prey. On to the next simulation. The age limit stops the predators from living forever, but not before they've eaten all the prey. In nature, I think it'd be unlikely for predators to drive prey to extinction so quickly. There'd probably be at least a few prey who'd survive. So whenever there's only one prey left on a square, I'll give it a good chance to survive predator attacks. This is the first simulation where the prey don't die out, but their population increases until my computer freezes. In nature, there are limits to how many individuals of a species can live in the same place. For example, prey need to compete with other prey for food, and predators need to compete with other predators for territory. This competition within species limits exponential growth like we see with these prey. Past a certain threshold, I'll make it less likely for predators and prey to give birth. This will be proportional to their population size. Now we see oscillations, even though they aren't as obvious as the graph from the beginning. Though I see an improvement that could make them more visible. The code tells prey to move towards the squares with the lowest chance of being eaten by predators. This leads to very large amounts of prey being on the same squares, because the more prey there are on a square, the less chance a predator can eat them. But I'd like there to be some variation in movement, so I'll add a chance that both prey and predators move in the non-optimal direction. And with these changes, the oscillations become pretty obvious. Let's just appreciate them for a second. So, what did I learn from this? This video showed a clear progression in the graphs with each change I made to the model, but I actually ran into a lot of problem balancing the model along the way. Even this final model is delicate. Slightly changing a variable can break the oscillations and cause a species to die out. For example, here's what happens when I lower the prey birth rate. This makes me wonder, how many predator-prey relationships existed in nature that we never knew about because they didn't have the right balance? And how delicate is the balance of the predator-prey relationships we know of today? I'll end the video with a bonus simulation. I was curious about what would happen in a freeway model that acts like rock, paper, scissors. In this case, red eats blue, blue eats yellow, and yellow eats red. I don't know of any direct examples of this in nature, but it makes for a great visual.